let's talk about some acids and bases. So, let's look at the difference between strong versus weak. What do you think it means to be a strong acid versus a weak acid?
Strong acids can break apart more depth of
That's the misconception. It's a bad label. We'll see in a little bit. So, a strong acid is an acid that completely disassociates in water. And remember, disassociate means, and completely and disassociate means 100% of the molecules become ions. Disassociate means to become an ion, and completely means 100%. A weak acid is an acid that does not completely become ions. It's an acid that does not completely disassociate. And this is the exact same definition for strong base and weak base. So it's the same thing. And to be called a weak acid, it doesn't matter if only 1% of the molecules disassociate, turn into ions, or 99% of them. As long as it's not 100%, it is a weak acid. So, common strong acids: hydrochloric acid, sulfuric acid. A bunch of the most common ones we deal with are strong acids. Let's look at this weak acid. So some weak acids. Vinegar. Vinegar is a weak acid. You can get vinegar on your skin, no big deal. But this is where the danger lies in the word weak. Just because it's weak doesn't mean it's not dangerous. Hello? I also went and count, and I think there's enough people absent today that doesn't matter anyway. Alright. Bye. Miss Parrish has like 12 students. I have 16. That would be like almost 30 students in here 7th period. Which I only have like 20 desks. If you have Miss Parrish, unless they finish during this period. But let's look at hydrofluoric acid. Hydrofluoric acid, very, 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 very dangerous. Just because it's called a weak acid, meaning that not every HF molecule turns into H plus and F minus. But as soon as this one breaks down your skin and bones, then more of it will disassociate. So as the acid is consumed, more of the acid will start breaking and disassociating in ions, and they can attack you. And as they are consumed, more of the rest of them will do it. So, and if you get a drop of this on your skin, you won't feel it. It won't hurt. After an hour or so, you'll be in some of the most intense pain ever, as your bones begin to boil and dissolve, and starts making very poisonous and toxic stuff inside you, and you'll probably end up losing a hand or arm if you get a drop on your finger. Yeah, probably maybe just a hand or a finger. It's very painful and way to die, and it doesn't take much on you before you basically the only option is to cut off the limb before it spreads up. And even then, the toxins and stuff it's going to be doing, you'll might still die. You do not want any of this stuff to get on you, period. So just because it's a weak acid doesn't mean it's not very strong, or I should say not very powerful. So an example is 1.125 molar nitrous acid. Its formula is HNO2. This is a weak acid. Looking up the stats on it, 6.5% of HNO2 molecules will turn into H plus and NO2 ions. But if you put anything, I looked this up before I made homework because I need to make very sure whether or not titration depends on. I know it does depend on weak versus strong, but the calculations don't matter. It's still you write your equation and see what ratio it is, and it'll still work out. That's because when if 6.5% of them produce H plus ions, if any of the ions are used up, it enables more of this. So this concentration of ions stays constant. So if you have some water and 6.5% of it of the HNO2 are H plus ions, and you remove some of the H plus, then the remaining percentage of HNO2 will break down until you get this ratio again. Make sense? So it's going to keep this ratio throughout it. So what is an acid? What is a base? There are 3 different types of hydrogen. Acids. That's just a nomenclature for it, though. So first, let's talk about H plus ions. The first guy who studied acids is Arrhenius, and I have no clue if that's correct. He gave the definition: an acid is something that increases the concentration of H plus ions. And here I'm going to have to modify his original definition. Later on, we tested this. What is an H plus ion? What is it really? It's just a proton. A hydrogen atom has 1 proton with an electron spinning around it. And if we remove that electron, it becomes just a proton. Protons are very unstable by themselves. They will go and latch on to anything. For example, water. And this ends up making H3O plus. Hydronium ion. So H plus really doesn't exist by itself. It's always H3O plus. So the more technical definition is H3O plus hydronium ions. So it's anything that produces hydronium ions is a more accurate definition of it, of its description. But for the most part, we can always assume it's H plus instead of H3O plus for doing math and such. It works out the same way in most cases. And his definition of a base increases the concentration of OH negative ions. So hydroxide ions. And this is the strictest definition of an acid and a base. It means it has to have H plus ions and it has to have OH negative ions to be an acid or a base. The most common accepted definition of an acid and a base comes from, I do not know how to pronounce this name, Bronsted, I believe. I don't know how to pronounce the O. Lowry. His definition of an acid is more general. It is something that donates a proton to another molecule. Arrhenius basically says it produces H plus ions. But what if we had something that wasn't ionic? That doesn't produce ions, but still gives up an H plus to something else. Still gives a hydrogen to another molecule. In Bronsted-Lowry's definition, that it would be considered an acid, but would not be considered acid in this older definition. Likewise, a base is something that accepts a proton or a hydrogen atom from another molecule. So every single Arrhenius acid is a Bronsted-Lowry acid. So this just generalizes it to a broader definition. And last week we have the most broadest, most general definition, and that would be Lewis' definition. Lewis' definition is an acid. Acids are electron pair receptors. While bases are electron pair donors. Do I have that backwards? A Lewis acid is any species that contains an empty orbital which is capable of accepting an electron pair. So yeah, they are acceptors. So using this definition, NH3 would be considered a Lewis base. It would not be considered an Arrhenius base because it has no OH ions to produce. So we would consider ammonia to be a base under the Lewis definition. And let me see. It's also a proton acceptor. So it does make the definition of a Bronsted-Lowry base too. So NH3 would be a Lewis base, a Bronsted-Lowry base, but not a Arrhenius base. Because it does like to receive a hydrogen ion to become NH4 plus ammonium. It likes to receive an H plus and thus making it a base. Just like OH likes to receive an H plus to make water. So this is considered a base because it accepts this. Another interesting thing, so looking at sulfuric acid. So acids have something called a conjugate pair. Sulfuric acid is a strong acid, So 100% of it is going to ionize into H plus and HSO4. You might know the formula is H2SO4. This right here is a weak acid. So just because it's an ion doesn't mean it's not acidic or basic. This is a weak acid. It can also split off into H plus and SO4, two negative ions, but it doesn't do this 100%. Don't fall asleep. Chad? Alright, let's do some examples. So 250 milliliters of 0.125 molar strontium hydroxide solution is neutralized with 5 molar perbromic acid. What's the chemical formula for strontium hydroxide?
Sodium hydroxide is
H or OH negative. Strontium is in what group? It's in group 2. So that gives it what charge? So that means it's... Alright. And perbromic acid, what's its formula? So there's no hydro. No hydro means it's an oxy acid. Contains oxygen. Ic tells us it's going to end with ATE. And per means what? Add an oxygen. So we know bromate is BrO3 negative. So perbromate will be BrO4 negative. And the acid tells us it's going to have H plus with it. That's a 1-to-1 ratio, so it's HBrO4. H with the hydroxide is going to make water. And the strontium is a 2 plus, and this is a negative, so we need 2 of those per bromate. So we have 2 bromine over here, so we need 2 over here. We have 4 hydrogen, so we need double the hydrogen. That's balanced. So the ratio is 1 to 2. How many moles of strontium hydroxide do we have? So we got 250 milliliters. We know our conversion factor is 1,000 milliliters to 1 liter. That gives us 0.25 liters. And we know the molarity. The molarity is 0.125 moles per 1 liter. Liters cancel out, giving us moles. So that's 0.03125 moles. How many moles of perbromic acid do we need? Yes, so it's a 1 to 2. We got to multiply this by 2 to give us 0.0625 moles of perbromic acid. Thus, the final question is, how many milliliters of bromic acid do we need to add? A per bromic acid. Do we need to add? And we know that it is a 5 molar solution. So we're given moles, 0.0625 moles. And we have a conversion factor of moles to liters. 5 molar tells us we have 5 moles per 1 liter. But we want to answer in milliliters, so 1 liter is equal to 1,000 milliliters. Liters cancel out, moles cancel out, giving us milliliters. And thus we need 12.5 milliliters of perbromic acid to neutralize, and this is 5 molar perbromic acid, to neutralize 250 milliliters of 0.125 molar strontium hydroxide. So let's talk about concentration. So the various concentrations we can have is obviously molarity. Molarity is grams solute. Molarity is moles solute per liter of solution. 1 liter. We can have 2 different types of weight percentages. Weight per weight. I don't like the fact they use the word weight. It should be M per M because it's mass of solute per mass of solution. But usually, as long as you're on Earth, it's still proportional. Weight to weight is the same as mass to mass ratio. We have another weight percentage. Weight to volume, and that's mass of solute per volume of solution. This is usually when you're adding a solid to a liquid. And we have a volume percent, where it's, and this one's also usually done for liquid to liquid. But it doesn't have to be. It could be either. R. And volume percent volume per volume, volume of solute per volume of solution. And this one is generally always liquid added to another liquid. And one last one, the percent acid or percent acidity. Spelled it horribly. And this one is usually given as mass of solute in grams, and all these are grams. And this is all milliliters. Per 100 milliliters of solution. So, for example, when you buy ammonium, which is considered a Lewis base, let's say you buy an ammonium solution, that is 2%, eventually find out it is weight by weight measured. And the solution density, you can easily calculate. Measure the volume and the mass, and you can get 0.957 grams per cubic centimeter, or 0.957 grams per milliliter, because cubic centimeters and milliliters are the same. So the question is, what is the molarity of the ammonia solution? So concentration doesn't depend on how much you have. It's always good. Just assume a random amount. I always choose 100 milliliters. It might be easier to just guess 1 liter and work with that. I always just assume 100 milliliters. Question is then, how many grams of ammonia do we have? Well, we have a ratio of grams to milliliters. We know that 100 milliliters has the ratio of 0.957 grams per 1 milliliter. Thus, it has, in 100 milliliters, it has 1.914 grams in 100 milliliters. My bad. The total solution has 95.7 grams. So the total solution mass is 95.7 grams. Because the density of the final solution is 95.7 grams. Because we know the density is 0.957. So this is the total mass. And we know that the ratio of mass of ammonia to total mass is 2%. So the ammonia's mass would thus be 2% of 95.7 grams. So that's 0.02 times 95.7 grams, which gives us 1.914 grams. And we're trying to solve for molarity. Molarity is moles per liter. And we can get a ratio of grams to moles. We know ammonia is NH3. N has a molar mass of 14.000674. Hydrogen has 1.007943. Yes. Mm-hmm. And thus the molar mass of ammonia is 0.030569 grams per mole. So we have a ratio to convert between grams to moles, and we know how many grams we have in our 100 milliliter solution. So we can get a final answer, 1.914 grams and 100 milliliters is what we have. We can convert grams into moles, 17.030569 grams per 1 mole. That is grams. And we know that there is 1 liter and 1,000 milliliters. That gets rid of milliliters. And now we're left with moles per liter, which is molarity. So it is 1.124 molar solution. Make sense? So we're given the ratio of, for example, we know for every 2 grams of ammonia, we have 100 gram solution. 2%, that's equal to 2%. And we know that 957 grams of solution is equal to 1,000 milliliters of solution. That's your density. Thus, we can use the fact that we can make up a number, 100 milliliters of solution. So we just make up 100 milliliter solution to work with. We can use this conversion to get grams of solution. And we can use the fact that we can go from gram solution to grams ammonia because we know it's equal to 2%. And then we can figure out molar mass, which is grams of ammonia to moles of ammonia, and figure this all out. Any questions? Alright. I'm giving out homework. You can work on it today and tomorrow, but if you don't finish it, I want it when we come back after summer break.